So it contains three functions, right? Expression value, term value, and factor value. So in here, there's one tricky thing here is I declared this function from the beginning, right? This is the declare of these functions, like declare a variable, but not initialize the content, right? I'm declaring there are three functions. Why do I do that? If I comment this out, there will be some errors, right? While compiler is analyzing expression value, it doesn't know what is term value, right? Because you haven't defined it yet. You never say what is term value, right? In order to do that, you need to give compiler some hint, right? You need to tell the compiler, okay, this is a term value. Only the signature is enough. You can tell it, okay, I'm getting the expression, then I'm getting a position, right? So you can give a expression, give a position. And it returns an integer so that you can assign to integer, right? So you need to declare it first, then use it, right? So that is helping the compiler to know what is the input and output of your functions. And similarly, as you can see here, right, factor value, it never sees factor value. So it doesn't know how to compile this code. So what you need to do is you should define it here, right? Declare it here. Only declare the interface, right? Input and output. And similar here, we can define it here. But indeed, this one is not needed because expression value is the first one you defined. So while the compiler is compile term value or factor value, it already knows what is expression value, right? Because it's defined before factor value and term value. Try that, all right? But the easiest way is declare all the possible functions in here, right? So that they are using each other, right? While you are defining expression value, it's using term value. So because term value is defined after, so I declare it first, right? Declare it first, so the compiler will know it. All right, so how to use this? This is how we use it. We give a string, right? 3 plus 4 times 5, and also the position. What is this position? The position is the position in your string which haven't been analyzed yet, right? So at the beginning, position 0 is the position you haven't analyzed yet, which is pointing to 3, right? Then you go to the expression value. So in your expression value, right, you first call term value. As you can see, this position is a reference. Term value, this position is also a reference. So when you are evaluating your term, you will also change the position. Everything you have already analyzed will be the past, right? So the position is pointing to whatever character you haven't been analyzed yet. So that is the key idea. So every position here, when the function finishes, position pointing to the place where it hasn't been analyzed yet. So if my input is 3 plus 4 times 5, if I run it, I can step into it. Let me ask you this question. If I run the term value, what would be my position? Now the expression is 3 plus 4 times 5. Current position is, wait a minute. Current position is 0. The value is 0. Current position is 0. And the expression is this one, right? My question is after term value, what would be my position? Because the position is passing to term value using reference. So term value will change the position, right? So what would be the return value of position after running it? It should be 1, right? The first term value will eat the 3. Without looking at the details about how term value is implemented, you are expecting the position to become 1. You are expecting it to become 1, right? Become 1. And then you are looking at expression of 1, whether it equals to plus or minus, right? If it's a plus or minus, we will get into this loop. This loop, we are expecting more term values, right? So when we run it, we can get the up. Wait a minute, where is it? We are getting the up. Up is a plus, right? We are getting this one. And now we are changing the position. The position is, because we already consumed this plus, now position becomes 2. And we are pointing to 4, right? We are pointing to 4. And if you go into this term value, right, it will also consume some part. And when this function finishes, the position is also modified, right? So what is the position after I run this line? What is the position after I run this term value? Without looking at how term value is implemented. 4 times 5 is a term, right? So it should point into the end, which is a \0. It's 0, 1, 2, 3, 4, 5, right? It should be 5. Let's do it. And now position becomes 5, right? It's pointing to the end of your expression. You have already finishes it, right? The first term value get 3, second term value get 4 times 5, which is 20 here, right? 20 here. And now, because of this operation is a plus, so you do a result 1 plus result 2. And because you are getting to the end, so you're returning, right? So if you are trying to debug this expression value, right, you should get rid of the details about term value, right? Just get the interface. Get the interface. You should be able to implement expression value without looking at how term value is implemented. That is the abstraction, right? Also, when you are trying to implement the term value, you should forget about how factor value is implemented. And similarly, in factor value, right, you should forget about how expression value is implemented. And you can look at this code, because we get rid of the seeing peak and seeing get, you should be able to fully understand them. The only harder to difficult to debug thing is the position, right? There are many places I use the ++ position, and sometimes I try to write them in this way so that you should be able to figure out by yourself. So that is the mutual recursion part, right? So go back and check this. I also updated my slides. I updated my slides to get rid of the seeing. All right. Any questions? No? Good. And the last time we have talked something about the Fibonacci, right? Fibonacci, which is the efficiency of recursion. So in the efficiency of recursion, we use this example. Let me copy this to my Xcode. Delete them because the code is already in Canvas, so I don't need to keep it. Let me quickly remove all of them. Right, this is our Fibonacci, and we are trying to figure out how many times it's entering the same function, right? Wait a minute, it's still running. Let's call it a Fibonacci of 3, maybe 4 is better. When it's running, you can see how many times it's entering Fibonacci 3, Fibonacci with n equal to 2, right? The first time entering 2, second time entering 2, right? So this Fibonacci has the efficiency issues because of 2 reasons. First one is duplicating, right? Because the first time, if you look at this picture here, if you are computing Fibonacci of 6, you have two function calls, Fibonacci 5, Fibonacci 4. Inside Fibonacci 5, you have two function calls, Fibonacci 4 and Fibonacci 3. So as you can see, it has many function calls. If the number is n, they are in total 2 to the power of n numbers of function calls. So because our operating systems wouldn't allow you to do so many function calls, so there will be a efficiency issues. Also, because the recursions create a stack for every function, right? So that will be a nightmare. And so how can we improve it, right? How can we improve it? First one, we can get rid of the duplicate computation, right? Fibonacci 4, Fibonacci 4. Why don't we just compute once? Why don't we just compute once, right? So there are some scenarios in the existing ones. Let's see, how can we improve it? All right, so first idea I want to talk about is something we call dynamic programming. Let me introduce dynamic programming, this idea. So this idea is, this one is different from what we have learned about sliding window. So in sliding window, we have to remember correctly, right? What is my previous? What am my previous? And remember to update them. So sometimes it is error prone, right? Sometimes it's hard to make it right. So in dynamic programming, this one is very easy. This one is using a vector to remember the result. All right, let me call it fib. Let me include my vector library. So what I'm trying to do is, let me first give the initial values of two elements. Fibonacci of 0 equal to 0, Fibonacci of 1 equal to 1, right? Or maybe I should do it this way, and so that it is clear. Let me initialize it with n number of zeros. And let me give Fibonacci of, maybe not, maybe that one is better. Just to give the initial values 0 and 1. Now this vector contains two elements, 0 and 1, right? And in here, we have making sure Fibonacci of 0 equal to 0 and Fibonacci of 1 equals to 1. How can we compute Fibonacci of n, right? So what we need is an for loop starting from 2 and end with n. Maybe end with equal to n. What we are trying to do is Fibonacci dot push back a new value. The new value is Fibonacci of I minus 1 plus Fibonacci of I minus 2. At the end, I'm returning Fibonacci of n, right? So using this way, we are wasting a vector, right? If n is 1,000, we are wasting a vector. The size is 1,000. But we are making sure our implementation is much easier to understand, right? Because the Fibonacci, if we can making sure Fibonacci I minus 1 equals to Fibonacci of I minus 1, right? And this one equals to Fibonacci of I minus 2. We are generating a Fibonacci of I, right? Then we push back into our fib. Then it contains all the Fibonacci values, right? Starting from 0 to n. This is the factor. We are trying to remember all the results. And so at the end, we can returning just the last element. That's why I'm using less than equal to, right? That's why I'm returning less than equal to, because it requires you to remember all the values starting from 0 until n. So there are n plus 1 elements in this factor. So this one is slightly better than the sliding window, right? The idea is because this one is much easier to understand, right? This one is much easier to understand by writing in this way. You don't need a sliding window to take care of all the scenarios. So let's see if we can compute it efficiently. let me give it 10,000, right? Wait a minute. I'm calling the original version, right? Fib. If it's 1,000, my machine will broken. So let's do this, right? Dynamic programming version. If we run it, it's very fast, right? We can quickly get in the result. It's because first one, we are not wasting our time duplicating the computation, right? What is duplicating the computation? Fib4 is only computed once, right? Fib3 is only computed once. We're not wasting our time duplicating these computations. In the original recursive version, it is duplicating the computation, but we are trying to making sure every element is only computed once, right? Only once. So that's one. Another is because it don't have a recursive call, right? We get rid of the time for creating stack, removing stack, and so on. So this one, dynamic programming is a very important concept. It can help you to avoid this duplicate work by wasting some of the space to remember the pre-computed results. So that is a concept. But anyway, let's go back to here. This is a recursion, right? We have tried this. It has duplicated things. And last time we have introduced this one, right? Using previous and previous to compute the f of the new, which is the Fibonacci of n. So this one is more efficient, right? Compared to our dynamic programming version, because it only contains 3 integers. If n is too large, right? It only contains 3 integers. We are not creating new one. But in our dynamic programming version, if n is 10,000, it contains 10,000 elements. So this one is more efficient in space and time. But dynamic programming, that one is much easier to implement, right? And easier to think about. So that is some of the difference. So if we compare these two, right, you should be familiar with these two names. First one is called a recursive, which is a recursion, right? Function calling a function itself. And iterative, you should be familiar with this name. Iterative means using a loop, right? Using a for loop, while loop, not using a function call to implement this. So if we compare these two, we say iterative version is much faster than recursive version because of the stack issues, creating a stack, right? Because each time when there's a function call, we create a stack. But there's one exception. It's called tail recursive. So tail recursive means there's nothing left after the recursive call. Here is an example. If my factorial helper is the last statement of your recursive function call, right? This is the last statement. If this function returns, you can immediately return it. So this is called a tail recursive. And for tail recursive, our compilers are very good at optimizing this code. They will not using it's different from a typical recursions. Compiler will generate some code that's very efficient. So you can ignore the overhead from the recursions. But there's a but. For every tail recursive, it should be very easy to convert into loops by hand. All right. So if you see this kind of code, right, it's recursive at the end, you should be able to convert it into loops. It should be very simple. All right, try that. How can we convert this one? Because it's factorial, it's very easy to convert. We are saying for every tail recursive, it's very easy to convert into loops. You should do that. And we say whenever possible, try to use a loop to implement your functionalities. But there are quite a few problems that is very, very hard to solve using loops, but it's very easy to solve using recursions. And also writing the code is quite simple, right? Writing the code like the Fibonacci, even the Fibonacci code, right? Writing in that way is quite easy to understand using the recursions. But there are also some problems like this one. It's extremely hard to solve using loops, but it's very easy to solve using recursions. It's called towers of Hanoi. So it's a problem. Like we have different numbers of different size of plates, right? Assuming there are n of them. How can you move from the first pair to the last one? So that is the question. You cannot put a large plate on top of a smaller plate. So that is the constraint, right? So how can you do that? Think about it. How can you do it in a loop, right? It should be quite difficult to write it in that way, but let's do it first by hand. Let's figure out how we can move the plates. So this is the first one. This is the second one. This is the last one. Let's call it A, B, and C, right? Let's give the plate also some name. Plate 1, 2, 3. How can we move it? First one moving the smallest to maybe to C, right? A to C. Let's call it A to C. Because there's only one possibility of moving, right? When you write A to C, it means moving the smallest to C. So it becomes 2 plates in here, 1 plate in here, right? Then you say A to B, then it becomes largest, middle, and smaller, right? And then what you can do is C to B, right? Largest, too small. Then A to C, too small, largest, right? So you can do on and on and on. Next is moving the smaller into A and the middle one into C, then moving the smaller into C, right? This is what we do by hand. So first, let's consider how can we solve this problem, right? How can we solve this problem? Assuming we have a function called that will generate this bunch of instructions as told you how to move. Let's call it Hanoi. Assuming this is the function to move it, how can we move the using recursion to solve it? Let me create a new one. 1, 2, 3. Empty, empty, right? In recursion, we said we need to make the problem smaller. How can we make the problem smaller? Instead of moving 3 plates, we move 2 plates, right? So when we are doing this, implementing this function, we assume it can move, it can already move, if it's n plates, it can already move n minus 1 plates. Assuming our function can already implement, can already move n minus 1 plates, right? It's a recursive thinking. Assuming we can our function can work for smaller problem, right? How can we use this one to construct the result for a large problem? This is how we do it. Assuming we can move n minus 1 plate, we move the n minus 1 plate to B, right? Move n minus 1 plate from A to B. That is our first step. Assuming it's done. Assuming it's done, what can we do? We can move from A to C. Right? After the last one is in C, what we need to do is Hanoi n minus 1 plate from B to C. Right? Then we are done. So that is the recursive thinking, right? To solve a large problem, we split them into smaller problems. If we can solve the smaller problem, our larger problem is solved. So it's very similar to, you can verify this one using 2 plates, right? If n equal to 2, if we already know how to move one plate, we move one plate from A to B, then move the larger one from A to C, then move the one plate from B to C, right? If n equal to 2 is correct, then we can verify how about n equal to 3, right? If n equal to 3, if we already know how to move two plates from A to B, then we move the remaining from A to C, then move the two plates from the intermediate one to the final destination, right? So that is the thinking process. So how can we implement it? This is a Hanoi, right? M plates, and should be some integer. We have to specify the first or the start position, some of the intermediate plate, and also our end, right? So what we should do is we need to move n minus 1 plate from our start position to the intermediate state, right? Intermediate place. And now the end should be in the middle. We can use these three pairs, right, to move from start to intermediate using the other one as the intermediate state, right? Using the end as the intermediate state. So you can use that one to put n minus 1 state into the intermediate one. That is first step. Second step is, let's just see out. I'm trying to move plate n from start to end. Right? We are trying to move plate n from start to end. And what's the remaining? Remaining is do this again, right? Moving the n minus 1 from, now this is your start. This is your end. And some of the intermediate one you could use is in here, right? Now we have finished this Hanoi part, the recursive part, right? What is remaining? What do we have to do next? The special case, right? Special case for recursion. When should it stop, right? Otherwise, it will keep running. So we should stop when n equal to 1, right? When n equal to 1, it should be very easy. Let's see. I'm not sure if it can work. Move plate 1 if there's only one plate. Maybe I should forget about these signals. Anyway, let's see. Let's move them. Move plate from start to end. Move plate from start to end. Then return, right? If n equal to 1, we just move it, we are done. And more than 1, making the problem smaller, right? Becomes n minus 1 problem. Then move the final one, then move the remaining n minus 1 plate. So let's do it. Let's do this. How about two plates? Two plates should be easy. I should specify start from A to B, finally getting C. Move plate from A to B first, right? The smaller one. Then move the larger one from A to C. Then move the smaller one from B to C. Right. So that's this one. How about 3? We could have from A to C, then A to B, then C to B, right? AC, A, B, C, B. Let's see. AC, A, B, C, B, right? Then AC. That is the output, then AC, right? You can keep on and following these steps, you will be able to move all the plates from the first pair from A to C, right? So that is the basic step, even if it's maybe It's 6. How about it's 6? Right, it should be quite long. It's too long. Anyway, so that is the Hanoi problem. As you can see, this one is not a tail recursive, right? We said a tail recursive means if this one is the last statement for your recursion, it is tail recursive. There are 2 recursion calls in here, so it's not tail recursive. This one is quite slow. If you want to give it 100, it will be quite similar to what we have done for the Fibonacci problem, right? Fibonacci has 2 Fibonacci calls. Fibonacci call, Fibonacci call. Here's the same. Hanoi call, Hanoi call. So that would be a problem if the number is too large, right? So you should try with some smaller ones and try to figure out if this one is correct. So any questions on it? No? Yeah, someone might have confusion, right? This is the only place I'm doing cout. So they would think, okay, if it's, for instance, if it's, for example, 4, the first thing it is printing is A to B, right? Someone might have confusion is, okay, in here, this is the first print statement, right? It should print from A to C instead of from A to B, right? So that is their confusion. Indeed, there are some of the recursion call before this cout. So the first cout should come from the first recursion call, right? Instead of this cout. So we should keep track of which one is calling first. All right, if there's no problem, let's continue here. So these are the kind of problems that is very hard to solve using iterative versions, but it's very easy to think recursively, right? But you could also solve this one using something like the dynamic programming or something. You can try that. All right, so next exercise would be merge sorting. So we have talked about bubble sorting, right? What is sorting? Sorting is making some numbers that is scrambled, right? 1, 3, 2, right? Making them 1, 2, 3. So in our bubble sorting is indeed the easiest to implement one. So in bubble sorting, we are trying to swap from neighbors. But merge sorting is having the idea about, we sometimes call it divide and conquer. So we first divide the problem into 2 smaller problems and then conquer them, combine them into the final solution. So if you think about this is a function call, right? Then we split the whole array into 2 parts. First, sort the left half, then sort the right half. Once all of them are sorted, combine them, merge them, becomes the final one. All right, so this is the merge sorting. So how you would implement merge sorting is, for instance, I'm not going to write down the whole part, but I would do something like here, merge sort, right? Assuming we are trying to implement a merge sorting. Our input is a factor of integer array, right? Let it be reference because we want to change the order of integers inside our factors. And let's call, let me call this one sort, and then let me call merge sort. I believe merge sorting is already implemented in our C++ library because it's merge sorting is the most efficient way to sorting an array. Let's say starting from 0 to factor.size minus 1, right? So that, remember the helper function? Remember the helper function? Sometimes we need the range, right? Starting position and end position. This is the interface we want to give it to the outside. This is something we are trying to make it recursive, right? Like the binary search, we need to find out who is in the middle. Start, class, end, divided by 2, right? You should merge sort the first part, then merge sort the remaining part. Then you need to try to merge left and right. It should be merge sort. All right. So this is the way you should do. I left this one so that you can implement on your own. So how can we, wait a minute. Let's first specify the end position, right? The special case. What is the special case? If start is greater or equal to end, right? We can just return. Why is that? Because if it only contains one element or zero element, we can just return. Otherwise, we do merge sorting, split into two, then merge the left, merge the right, then merge sort the left, merge sort the right, then merge them, right? So how can we do it in here? I will explain it a little bit so that you can go back and implement it. Assuming I have a vector, let's give it some random number, 1, 2, 5, 3, 8, 4, 1, 2, 3, 4, 5, 6, right? Then we split them into two. Split them into two, and assuming our recursion could sort the left part, right? Don't pay attention to how it is sorted. Assuming it can sort the left part, 1, 2, 5. Then the right part, 3, 4, 8. How can we make them a sorted one for the whole array, right? In order to do this, we need to keep track of 2 pointers, right? Let's this one call it left, this one call the right. We compare left and the right. If left is smaller, we put it here. Then this one goes to the next part. Then compare which one is smaller, right? If 2 is smaller, put it here, increment left. Then compare who is smaller, right is smaller, becomes 3, goes 1 step, right? Then compare 5 and 4, who is smaller, 4, then move on. Compare who is smaller, 5, then 5 is here, right? Then the remaining one is 8. So this is the step of how could we merge? How could we merge 2 sorted arrays and it becomes 1 final array, right? So this is the basic idea of merge sorting. You should be able to do it offline. It's not that difficult, just comparing, have 1 pointer pointing to each one, then comparing which one is smaller, right? Whichever is smaller, copy it to somewhere. So that is the basic step. And also, if you cannot do it, you can Google online. There are so many different implementations of merge sorting. You could check that because it is so useful, right? It's already implemented in many of the libraries. You could go back and check that. All right. So next topic we want to talk about is called the scope. So the scope is where the names or of a variable can be seen by others and also can be used by others, right? For instance, if we think about, where's my Xcode? If we think about this function, right? If we think about this function, because this array is defined inside of this function, you cannot use it outside of this function. I cannot use it in my main function, right? If I say fib, because I use the same name for this array and this function call, let me call it fib factor. Because this fib factor is defined inside this function, you cannot use it outside. You cannot use it in here. Fib fact dot push back, right? It doesn't make sense because there's no flip factor defined in here. This one is called a local variable. It's called a local variable. It's local just to that function. So we have local variable. We also have global variable, right? What we could do is, for instance, if I define another function, test scope. Let me see. If you define variable outside of your function, int a equals to global a equals to 10, then this global a could be used in here, could be used in here. Let's say if we assign it to 10, to 100, right? Then we call this test scope. And let this one be void. All right. If I only shows you this code, you would think, okay, this I should see out of 10, right? If I only show you this part of code, you should think this one only output 10. But because this one is global, any function could change it, any function. So in your main function, you could change it. In your test scope function, you could change it. So if you do this, you first assign global A to 100, then test the scope, you should output 100. Right? You should output 100. If I define this way, I define another local variable that has the same name as the global variable. It is 10. If I create another block, right? Remember the braces, it's called a block. I create a new one, give it to 20, and then I'm trying to see out, maybe make it more complex. Give it 30, right? What should be the output? First one, define it to 10, then define it to 20, then define it to 30, then I see out once, see out once. First result is 20. This result is 10. Right? This one is 20 because this is some temporary scope, a temporary block. When I enter it here, a new variable is defined called a global A. When I exit it, when I leave this block, when I leave this scope, this global A no longer exists. So this global A refers to this one, this global A, which is 20. All right. And also to make it more complex, how about I delete this part? Right. So let me draw it here. Let me draw it here. There are a bunch of scopes. The largest one is called the global scope. This is a global. All the functions, all the main function, any function you define will be able to access it. This is A here, right? A equal to 10. We have defined A equal to 10. And this is the scope for your test scope. This is the scope for your main function. So whichever variable you define in here, A equals to 10, another 10. Let me change it that future. If you define this A here, this A cannot be used in main function because it's not enclosing this scope. And also we have another scope, right, which didn't define any A, but output A. And in the middle, we have another scope defining A equal to 30. So this is the rule for finding out who is the variable. So when you are trying to read a variable, modify a variable, you first look at where it is defined, right? You first search for your current scope. This is your current scope. This is your current scope because it don't have any A defined. It is trying to go out. It's not getting into some other scope. It's getting out to the other scope, which is the test scope, right? It has A equal to 10 defined, then it will immediately output 10. If it didn't find any A, it will continue go out, then go out, then go out until it sees maybe the same name defined. All right. So this one is the global or local, right? There's only one global variable. All the others are local. But even in local, they have different scopes. They are defined in different blocks, right? You are defining in the smallest block. This one is in a relatively small block, and this one is in the test scope. So for this, it might be not that hard to understand. Let's do another one. So sometimes scopes are not so easy to see. Let's do this. Int A equals to 10. All right. Then let's do a for loop. A equal to 0, A less than 100 plus A. Let's do B equals to A plus 1. All right. Anything. What is A? What is the output? What is the output? 10. Any other answer? The answer is 100. The answer is 100. 100. It will be 10 if I define it in this way. Yeah, then this one would be 10. See the difference? If I don't, let me first do this. If I put an int here, inside of the for loop scope, you are declaring a new variable called A. So this A++ is applied to the new A you defined. It's applied to the new A you defined. It's not this A. But if you don't declare a new one, right? Then this one is the old A. This one is old A. It will look at this A. It will look at the scope outside of my for loop, right? It will find that this is the A, right? So this one will be, so this for loop will keep incrementing A, which is the A defined in the function scope, right? Then it will keep adding until it reaches 100, right? When it reaches 100, it stops. So this output is 100, right? Can I see out B in here? Can I see out B here? Can I see out B here? No, because B is a variable defined inside of this for loop scope. It's not a variable in the function scope. It's a variable defined inside of the for loop scope. So outside of the for loop, if you are trying to see out it, it's invalid. It never sees a B before, right? There's no B defined in this scope or outside of my scope. It's not defined. So you should pay attention to where this variable is defined. If it's defined, whenever there's a type plus variable name, it's a declaration, right? Declare a new variable inside of this scope. It will not work for outside of the scope. Similarly, if I define A here, right? This A, it only belongs to the for loop scope. It's no longer valid outside of your for loop. So that is something you should pay attention to. All right, so this is something for the scope. When we talk about the classes, we will see more examples. All right, any questions on the scope? No? All right, so let me see. All right, so that is this. Let me comment this out. So you can be here. All right, so there are mainly two types of variable scopes, right? First one is called local, another one is called global. Global is visible to the whole program, and the local is only for the block you define, right? What is block? Block is defined by a brace, right? Left brace, right brace, it's called a block. And everything defined inside of the block cannot be seen outside of the block. That is the basic idea. So this one, right? You should try this. The tricky thing is in here, right? You are creating some weird block here, right? Creating some scope here, defining an R, and then you are trying to see in R and use it after this block, right? Go back and check this, whether this R is visible outside of your block, right? It should be easy to test. So global variables, because it is defined outside of all functions, right? And also it is visible, modified, can be modified by all the functions. That's also why we said it's very hard to see here, right? If it's global A here and you are trying to output global A, you never know whether this global A is modified in some function or it is modified inside your main function, right? You never know that. So sometimes we would ask you to avoid global variables. Try to avoid global variables. Right? Global variables like this one, like the balance here, right? Let me copy this part of code. Let me copy it. The reason people use global variables is because they want to avoid converting this one to the parameters in function calls. So we would suggest you to write code like this, even if you want to change the balance outside of your function, right? We would prefer this way. Make this variable a reference so that if you want to change it, you can change it. You are explicitly telling others that this balance might be changed. So people have this, they have this anticipation, right? They could expect this balance to be changed after calling this function. They know it. But if you are defining it using the global variables, right, like this, you will never know whether this balance is changed or not changed, right? Or changed by this function or changed by other functions, you don't know. So that is something the beginner tend to do. They are trying to type less things in the parameter list, right? If you have more than, for example, four parameters here, you need to list all of them. They think it's time consuming, right? They don't want to type so many things, so they just put a global variable before. So whenever they want to modify it, they immediately modify it. Sometimes it's bad, right? But if you cannot avoid it, you just use it. But I would suggest you to avoid these kind of global variables. So you can look at it here, right? This is something the beginners tend to do. They don't want to use the parameters. And one student asked me if I put everything in my parameter list, this one would be too long, right? And in the future, we will learn, maybe next class, we will learn struct and a class, how they can be enclosed into just one variables and use all of them inside your functions. So that will be next class. So you can test this out, right? You have a global variable here, and you define some local variable with the same name. And if you want to see out it, right, you can see what is the output. So, and another important topic is about the lifetime. So we said inside a function, right? If you define some variable inside some scope, whenever the scope, when you exit this scope, this one will no longer exist. right? So we talk about this one, but how about we require something? For instance, we want to count how many times a function is called, right? Let's do it in here. Let it be void, called some f, any function. Let's create something called count. And each time this function is called, we increment your count, right? Then we see out f is called count times. If I call this function multiple times, what will be the output? What will be the output? You would output f is called 1 times. F will be called 1 times. F will be called 1 times, right? And let me put a blank space here. Yeah. So as you can see, all of them are 1. If you want to count how many times a function is called, you cannot use a local variable here. It is local. Whenever a function is called, it is created. It's creating a new version of variable each time you call it, right? Next time you call it, a new variable count is created. Next time you want to do it, a new variable is created. So someone would tend to, okay, how about we define a global variable, right? Will it work? Will it work? It should work, right? Because there's only one version of count. So it can work. First one, output 1. Second one, output 2. Last time, output 3, right? If it's global, anyone can modify it, and it's there. It's not destroyed after this function call ends. So you are always referring to the same variable, right? Now, because we said we shouldn't use a global variable, right? It's sometimes bad because anyone could modify this count. So you don't know whether this count is modified by others or not. So it's bad. Let's don't do this. Another way is called static. So instead of a global variable, if this variable is only used for this function, right? Instead of using a global variable, we use a static variable. Let's see what will be the output. Output is 1, 2, 3, right? So the way we use a static, the reason we do it is we want this function ends, but don't destroy this count variable. So no matter how many times you're calling this f, count will be created only once. The first time you create a count, second time when you get into it, you are referring to the same count, and you are not initializing it. You are not initializing it. It will only be initialized once. This line will be only executed once. So your function could use a static variable to count how many times this f is called, right? But again, you cannot access count here, right? If you are trying to modify count to be 10, you cannot do that. Compared to global variable, right? If it's a global variable, you can do that. You can modify count outside of your function. Anyone could modify your count. But if it's a static int inside your function scope, no one outside of your function could access it, right? No one could change it except yourself. Only you can change it because this is a variable defined inside your scope. No one outside could see it. So this one is some good way to keep track of how many times a function is called, right? This is a static function, a static variable that it can be used. It will exist until the end of your program. Where's the slides? Yeah. As you can see, it is initialized only once, and it exists until the end of your program. All right. let's look at how this one works. We are trying to remember, we are trying to get how many times a Fibonacci function is called. Redefinition, let's give it a new name to the f. Let this one be f, and this one be fib2. But one thing to notice is this cout is at the end of your function call, right? So you will do recursion first, then cout. You will do recursion first, then do cout. So this cout, you will see weird behaviors. Let me do it here. Fib2 of 4. Let's see how many times it's called, right? It's not incrementing from 1, 2, 3, 4, 5. It's doing 3, 4, 4, 5, 5. All right, because this cout is after your fib call, right? So when the 4 comes in, fib3 is called. Inside of fib3, this count is incremented. So your cout will never reach 1, right? It starts with 3. Go back and using a breakpoint to see why this is the output. It's not 1, 2, 3, 4, 5. It's 3, 4, 4, 5, 5. All right. If we put a 5 here, it is 4, 5, 5, 6, 6. Right. The total number is correct. The total number is correct. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right. Is it 9? Yeah, it's 9. So the total number is correct, but the output from the beginning is 4. Right? Try to figure out why this is the case. All right. So the main reason, let me repeat again, is because the cout is after your recursive call. So you will be able to see why this is the case. All right, let me go to our final exercise. This is a good exercise for recursions. It's called n-queen problem. So queen in the chess is someone who can attack anyone in the same column, anyone in the same row, anyone in the diagonal. So in these 4x4 board, you are trying to place 4 queens so that no one could attack each other. Right? This is the key idea. So what does it mean? If I put a queen in the first column, the third place, no one could put it in the third place anymore. No one could put this diagonal. No one could put it in this diagonal. So there are limited positions you can put another queen, right? There are some Wikipedia slides for that. Let me use Chinese to help you search for it. You can search for this problem, right? It's a very famous problem, and many of the math people who work on math, they are trying to figure out how can we quickly using math to get the results. And you can look at this one. All right, so this is the explanation about the whole problem. And it also shows how many solutions are there. Right? If it's 8x8, there are so many different solutions. All we need is just one solution. And here is a clickable link. You can click on this. You can click on this. It will give you the solutions for it. The key idea is called backtracking. The key idea is called backtracking. So let's start from an empty board, right? Then we are trying to put the first queen. You can put it in the first place, second place, third place, fourth place, right? If I put it in the first place, we are doing it column by column, all right? If I do it in the first place, in the first column, I'm trying to put the queen for the second column. I can put it in the first place, second place, third place, fourth place, right? We have 4 choices. Then we try if it's the first place, if we have a function that is checking if this place is valid, we can immediately see this one is invalid, right? Because these queens could attack each other, right? We said queen could attack whichever in the same row. So it will, one is also invalid because it can attack the diagonal. For the third one, at least for now, it's valid, right? We have done with 2 queens. Next, we need to put the third queen. Third queen could put into the first place, second place, third place, fourth place. And we need to check all of them, right? And we find out that this one is, all of them are invalid. Then we go back, then go to the fourth position, right? Like this. So it is indeed a recursive call, right? Our recursive call says we have a function. Let's call it n queen. This is the problem, right? This is the function we have done. This is the starting column. And we are trying to call it using with column 0. Assuming, right, we are trying to solve the problem for nq0. And how to make the problem smaller? Assuming we can solve the problem nq1, right? This is the range from column to the end of the column, and the column from the current column to the last column. This is the problem we are trying to solve. And we are trying to solve from 0 to the last column, the number of columns, right? To n, 0 to n. We are trying to put queens for all these columns. And assuming the problem becomes smaller, we are trying to solve 1 to n columns, right? Assuming we have a solution for this, what we can do is we try the first position, try the second position, try the third position, right? Then try the fourth position. Whichever way we choose, we call the recursive call nq1, right? If nq1 gives me one valid solution, this will be my solution. If nq1 says no solution, this one is no solution, right? So this is the recursive call. Get the idea? We are trying to put queen from column to the end column, right, to the last column. This is the recursive function. And right, we are making the problem smaller by moving these 1 to column plus 1 to the end column. Assuming this one returns some solution, and I have put this one in here, it returns some solution, it immediately returns. If it says no solution, it means the whole version have no solutions, right? So that is the key idea. Let's look at how it is implemented in here. So the first function we need to get is check. Let me copy it to Xcode. Wait a minute. Vector, right? So given a board, we need to check is a row and a column a safe place to put a new queen, right? That is the check we need to do. That is this cross or tick, right? Is it a valid one, invalid one? We need a function to check that. So that is this function. It should be easy to implement, right? Assuming I have already put queens to board from column 0 to column -1, right? Assuming I have already put queens to there, I'm trying to put a new queen in row and column. Put a new queen in row and column. What can we do? Because we do it column by column, we don't need to check for columns. The only thing we need to check is first rows, right? We need to find out if this row, if the the row has already occupied or not. If it's occupied, return false, right? We cannot put the queen in the same row, but we should choose a different row. That is, check if the row is already occupied. Second one is check if the upper diagonal on the left is occupied, right? Here is, wait a minute. If I already have my queens here and here, right? I'm trying to figure out, this is my board, and my row and the column are the one I'm trying to put the third queen, assuming the row is 0, column is 2, right? This is a column 2, column 2. This is a column 0, this is a column 1. I'm trying to put it in row 0, then it will violate the rows, right? The rows, row 0. The first queen is in row 0, so it will be false. If I'm trying to put in row 1, if I'm trying to put it here, right, then there will be a diagonal, right? It is the left diagonal, a lower diagonal on the left, right? Then we also check the upper diagonal on the left. So these are the two diagonals I need to check. This is a row I need to check, right? Is there any position already occupied by another queen? If it's yes, then it returns false, right? This is this functionality. You can check that. This is checking the upper left diagonal. This is checking the upper lower diagonal. And it returns true. Let's say returns true if it is safe to put the new queen in row column. All right. So this is this functionality. It only does is checking if the new queen in column and row, in row and column, are they safe to put it in the existing board, right? There are already some of the queens already there. So that is this function. We also have another function. Let me copy it here. Yeah. So whenever we are done with the isSafe function, we can ignore that, right? Let's look at how this one is implemented. Let me first erase them so that it can be fit in one screen. I don't need to scroll up and down. All right, this is the whole recursive call, right? What does it says is try to put queens from column to the end to the last column, right? So initially the column is 0. You are trying to put queens from 0, column 0 to the last column. And there's a recursive call, which is putting your queen, right, from column 1 to the end. If it can solve, it means you can solve. If it cannot solve, you need to try a different place, right? So that is the basic idea. So as you can see, it's calling. Let me go it step by step. So first your border comes in, then you're trying all 4 positions for current column, for your current column. For your current column, if the ith row is safe, you put it in ith row, right? You put it in ith row, then you solve it for the remaining columns. If it can solve, it returns true. If it cannot solve, you just keep trying the next position, right? You just release your current position because you put your queen in ith row, right? Then in next loop, you are trying to put in i+1's row, right? You are trying to one by one, try them all one by one and try to solve it recursively. then do it. So this recursive call is the whole part is called backtracking, right? Whenever you put a queen there, if there's no solution, you release this position. Then you put your queen to next position. Then you solve it again, then release it. This one is called backtracking, and it's also used in many of the chess games, right? If you want to build a program to feed, if you are trying to, for example, compare your program with the expertise, right? You will do it very deeply. It's called. Let me think about this one. Yeah, you can go back and check the news about how the large companies build machines to defeat this expertise in chess or in Go, right? How they do it. But backtracking is one of the main techniques. Try this position. If didn't solve, release this position, right? And it's basically doing sometimes we call it a depth first search. You are trying to find the solution, right? Using if we look at this one, you can think of it as a tree, right? You go it and then go to the deepest place. If in the deepest place you can find a leaf, you immediately return it. Instead, we have some problems that can be solved using breadth first. So instead of trying it first position, then trying the second column, you are trying the first position for the first column, second position for the first column, then trying the third position for the first column, and so on. So there are two different ways to traverse this tree. So if we think about this as a tree, but anyway, you don't have to understand them. But the basic idea is you should be able to solve this kind of problems using recursions, right? So any questions? We have finished almost everything about the recursions. And indeed, we have introduced many of the algorithm in here, right? First one is dynamic programming. Dynamic programming, you still remember dynamic programming? You trade the storage, right? For efficiency, for simplicity. That is dynamic programming, then divide and conquer, merge sorting, right? Divide and conquer. Divide the problem into two problems, solve the smaller one, then combine them. The last one is called backtracking. These are the three very simple ideas about how to solve these kind of problems. They are typically combined with the recursions, right? So yeah, I believe that's the